Computers are capable of playing a wide range of games, particularly those that rely on strategic decision-making and the application of heuristic search techniques. Such games are commonly classified as strategy games because they operate under well-defined rules and explicit objectives for each participant. Although strategy games are often associated with intellectual challenge, their ultimate value does not lie in winning alone, but in the enjoyment and engagement they provide. These games are closely connected to intelligence, especially the ability to analyze situations and solve problems effectively. A strategic game can be formally represented as a state space graph, in which nodes correspond to possible game situations or positions, and arcs represent the legal moves that transition between these states. A sequence of actions that leads from an initial state to a terminal state is known as a play of the game. Central to strategic games is the concept of a payoff function, which assigns numerical values to terminal states, indicating the outcome for each player. These payoffs define which paths through the state space result in gains or losses. Players act strategically by selecting moves based on an evaluation of possible future outcomes. This decision-making process is typically modeled using a game tree, which is similar to problem trees used in search algorithms. In a game tree, nodes represent positions associated with different players, and no single player controls the conclusion of the game. Each path in the game tree corresponds to a trajectory through the state space, and each node represents a specific sequence of moves leading to a particular game position. Research in artificial intelligence game playing focuses on developing programs that use local analysis to compete in zero-sum, two-player, deterministic games with perfect information. In such games, both players have complete knowledge of the game state, and there are no elements of chance. The game tree serves as a formal representation of the rules and possible actions, enabling the identification of optimal moves. To analyze game trees effectively, several techniques are employed, including local analysis, backup procedures, static evaluation, and heuristic evaluation functions. The efficiency and structure of the game tree are critical to the performance of a game playing system. So one of the most important optimization techniques is the alpha-beta pruning method, which reduces the number of nodes that must be evaluated. This method is based on the principle that a rational player will always choose the move that maximizes the value of their position, allowing the system to eliminate branches that cannot influence the final decision. Computers can participate in a variety of games, particularly those that require strategic reasoning and the use of heuristic search methods. These games are commonly referred to as strategy games because they are governed by explicit rules and clearly defined goals for each player. While such games are often valued for their intellectual demands, their significance is not determined solely by competition or winning, but also by the enjoyment they provide. Strategy games are closely associated with intelligence, especially the ability to analyze situations and solve complex problems. A strategy game may be modeled as a state space, where each state represents a possible configuration of the game, and each transition corresponds to a legal move. A complete sequence of moves from an initial state to an ending position is called a play. The outcome of the game is determined by a payoff function, which assigns values to terminal states and specifies the rewards or penalties for the players. This function defines which paths through the state space lead to favorable or unfavorable results. Decision-making in strategic games involves anticipating future moves and evaluating alternative possibilities. This process is represented by a game tree. in which nodes correspond to game positions associated with different players. No single player has direct control over the termination of the game. Each branch of the tree represents a possible continuation of play, and each node reflects a particular path taken through the state space. Artificial intelligence research in game playing focuses on creating programs capable of competing in zero-sum, two-player, deterministic games with perfect information. In these environments, all players have complete knowledge of the current state, and there is no element of chance. The game tree provides a systematic description of the rules and possible actions, allowing the program to determine optimal strategies. Several analytical techniques are applied to explore the game tree, including local analysis, backup methods, and static evaluation using heuristic functions. The design and efficiency of the game tree are crucial for effective performance. Alpha-beta pruning is a widely used technique that improves search efficiency by eliminating branches that cannot affect the final decision. This method relies on the assumption that players act rationally and always select moves that maximize their expected outcome. Artificial intelligence research in game playing focuses primarily on zero-sum, two-player, deterministic games with perfect information, such as chess and checkers. In these games, one player's gain is exactly equal to the other player's loss. There is no randomness involved, and both players have complete knowledge of the game state. The objective of a game playing program is to identify the optimal move at each stage of the game by analyzing the game tree. Because game trees can grow extremely large, AI systems rely on heuristic and approximate methods rather than exhaustive search. Local analysis techniques evaluate limited portions of the game tree, while backup procedures propagate evaluation values from lower levels of the tree to higher levels. Static evaluation functions are used to estimate the value of non-terminal positions when it is impractical to search the entire tree. These functions rely on domain-specific knowledge, such as material balance or positional advantage.